Polarons are a pervasive phenomenon in transition metal oxides. When you inject charge into a material, an oxide, instead of going delocalized into or dispersed into the material and assuming a metallic character, electrons can localize in a specific spot in the crystal and assume semiconducting properties. Polarons have a high impact or huge impact on the material properties, especially at the surface. For example, they can determine the crystal structure on the surface. However, it's not easy to study polaron because they are very mobile particles, and different configurations that they can assume during their hopping process can change drastically the material properties as well. So what we aim to do in TAGO is to propose efficient methods to study the different polaronic arrangement and the polaronic dynamics in the materials. How can we achieve this goal? We will start by considering traditional approaches like density functional theory calculations, and then move to novel techniques given by machine learning methods. We will also work in collaboration with the experimentalists, for example, from the project of Ulrike Diebold or from the project of Gareth Parkinson, where they will study the transition metal oxide and provide us with experimental data such as scanning tunnel microscopy images, where they can measure the charge of these electrons in their experiments. And we will of course need the support from the theoretical group of Georg Kresse, Georg Madsen and Christoph Del Lago for the advanced technique in the machine learning field. We would like then to collect all these data and try to propose novel methods that can address the stability of polarons with very efficient method, and also try to predict the property of the materials once we know the property of the polarons themselves. And for doing this, we will try also to investigate the experimental images by computer vision approaches.